All right. Hi, I'm Jayshua Nelson. I'm a freelance programmer. I work on websites and web applications, emphasis on the web applications, and I like programming languages, studying them, reading about them, all kinds of stuff. So we're talking about Rust today. I gave this talk to a friend of mine to get his advice, and he said that he liked it, but it needed a slideshow. And I thought to myself, well, yeah, that makes sense because every good presentation has a slideshow. So I made a slideshow. It has one slide, and this is my slide. So now we can know that this is a good show because it has a slide on it, and that's all we need. So we're going to get started. The talk is divided up into two sections. The first is going to be sort of an overview of the Rust tooling and ecosystem, and then the second section is going to be going over what's probably the biggest stumbling block for people learning Rust. It's going to be a little bit different than what you might expect in an introduction to Rust presentation. I'm not going to be discussing syntax or the type system or things like that, because all that stuff is pretty easy to find online. It's going to be in like the first 5 paragraphs of any blog post on intro to Rust. So I don't really want to waste your time with that type of thing. Instead, I'm going to be focusing on some of the points that don't always make it into those types of blog posts and things that might be a little bit more difficult to find or confusing. So we'll start with the first section right now then. If you go to the Rust website, right here, I think, yes, you can see it. If you jump over to install and download Rust up in it, that's how you install Rust. And what you'll get from that is a command line tool called Rust up. This tool kind of fits in the same space as NVM, the node version manager, or Python virtual environment. It basically lets you switch between different versions of the Rust compiler for different versions, for different projects which require different versions. So if I have a project that's running on Rust version 1.40 and another one that's running on Rust version 1.30, you can switch between them super easily. If we look at the current version of Rust that I'm using, you can see it's Rust compiler version 1.40 nightly, which is actually really old. It's almost a year old. And if you look up here, this is the other key bit of information, the host triple. It's called the host triple because there's 3 parts. There's the CPU architecture that Rust is going to be generating machine code for. There's the operating system that the standard library is going to be compiled against. So the standard library includes things like networking and multi-threading and features that require an operating system to implement. The other thing you might see here is Linux, for example, or unknown if that portion of the standard library is disabled. Then the third part is the linking tool chain that the Rust compiler will be using. So on Rust requires a system linker to function. So you can't just install Rust by itself. If you're on Windows, you'll need to also install Visual Studio or the GNU toolchain through like Cgwin or MSys2. And this indicates which of those Rust will be using. In this case, it's MSVC, which is the Visual Studio toolchain. GNU would indicate the GNU toolchain. If you look here, I have another host installed as well that I can switch between with Rust up. So I can tell Rust to generate WebAssembly code instead. And WebAssembly doesn't have an operating system, so the second part is unknown, and there's no linker or debug system for WebAssembly either. So the third part is unknown as well. Once you've selected the toolchain using Rust up, which will happen by default, it'll just pick the default one when you install it, then you'll also have the Rust compiler, which is Rust C. So if we open up a new Rust file, we can type a function. We'll just say hello world because that's what everybody does when they're learning a new language. And then we can compile it with Rust C, main rs, outputs to main exe. We'll compile it, and then we can run it, and we get hello world. So that's great. That's useful. You're never, ever, ever, ever going to do that. Nobody interacts directly with the Rust compiler itself. Instead, you're going to use another tool, which you'll get with Rust up, called Cargo. Cargo fits the same space as NPM, sort of. It manages dependencies, automatically installs them and compiles them, and it also manages projects. So we can go ahead and create a new project by doing init for new, -- bin to indicate we're creating a binary. The other thing you could see here is lib for a library that you would link against in another project, and then the name here. And that will just generate a directory for our project, which we can look at in Sublime Text. So you get a cargo toml file when you do that. This is roughly the equivalent of package.json. This is where you would list your dependencies. If I wanted to depend on Diesel, which is a library for interacting with databases like MySQL and Postgres, I could type that in right there. And then when I run cargo build, it'll automatically contact the package server to download dependencies and compile them all automatically, which is probably what you might expect to happen if you're coming from a place like Ruby or JavaScript. But Rust is probably the first systems language that really gets this well. C and C++ is not fun to work with dependencies with. Take it from me if you've never tried to compile a C program before. When you run cargo build, then you'll get a lock file. This just nails down exact versions of all of the dependencies. You'll want to commit that. And then you get a .get_ignore file. Cargo also creates your project as a Git repository automatically, so you don't have to worry about it, which is something that I have opinions about, but we won't talk about that. Instead, we'll go to the source directory, which is where we have all of our source code. It all goes in the source directory, and it automatically generates a hello world for us. Now, if we do cargo run, oh, I'm going to take out the Diesel dependency so we don't have to compile the whole thing. We get hello world printed out, and we're basically good to go. So if you take a look then at the directory after building, there's a target folder. This is where the actual binary gets placed by cargo. It's in the debug folder right here, cwitc.exe. You also get a PDB file, which are Visual Studio debug symbols. If you were compiling using the GNU toolchain, part of that host triple we looked at, you would get debug symbols that are compatible with GDB, the GNU debugger. Since I'm using MSVC, I get a PDB file, which we can use with the Visual Studio debugger, which I actually wanted to show you real quick because it's kind of difficult to find information on how to debug Rust code. So I just wanted to do a real quick demo of that because it's actually not that difficult. If you go down to your Visual Studio folder in the Start menu, there is a developer command prompt, which is basically the same as a regular command prompt, except it has all of the Visual Studio command line tools available, specifically devenv, which is the Visual Studio debugger. So we're going to run that. I've included it in my path manually because I use it quite a bit. If you haven't manually put this in your path, you'll have to use the Visual Studio command line tools, which we just looked at. So you're going to point it at the binary that you want to debug, which is in target debug. We just looked at that. It's the exe file. When you run that, Visual Studio will open up, and you can just drop the source file into here, and then it basically just works. You can set breakpoints, run the application. Here's our command window. We're stopped at the print line. If we step over, it prints out hello world, and then you can just continue from there. So that's basically debugging in 5 seconds. The last part, before we jump into the second section of the presentation, where we're going to be talking about lifetimes and ownership, is some websites that you definitely need to be aware of if you're programming in Rust. So the first one is rustlang.org. This is the Rust website. You can find links to pretty much anywhere else you might need to go on the rustlang.org website. If you go to Learn, there's a link right here to the Rust book. This is required reading if you're going to learn Rust. It basically goes over the entire language, everything you need to know to program in Rust, and it's pretty well written. I recommend reading that. If you go to the community link up here, there's a link to the forum, which is just a discourse forum that you can ask questions on. And then the other option for getting help from the community is this Discord server here. It doesn't really matter which one you pick. They're both very active, so just pick whichever one you're most comfortable with. Second website is crates.io. This is the equivalent of npmjs.org. This is where all of the packages for Rust are listed. Rust calls them crates. because it's called Rust, and so that makes sense. If we look up Diesel, which was the library for interacting with databases, it's right here. And you can see the current version, 1.45, and it also has the line that you can add to your Cargo TOML file in order to include this. And then the last website you should know about is docs.rs. So in order to understand how this fits into the ecosystem, we'll take a quick look back at Cargo again. Rust supports documentation at the language level. So if we have a standard comment, just like this, that's just a regular comment. But if you use 3 slashes, this is a documentation comment. So we could document main prints out hello world. And then if we run cargo doc on our project, cargo doc will go through all of the Rust code and extract out all of that documentation and package it up into an HTML file that we can use to view it. And it puts all of that in the target directory. That's where it puts everything. Here's our documentation. And if we look at index.html, we get our function main and the documentation for main right there, which prints out hello world. So that's what docs.rs does. Docs.rs goes through every package in the crates.io package system and runs cargo doc on it to generate the documentation. So if we look up Diesel again, we can see all of the documentation that was automatically extracted from the source code for this library. And there's actually one other really neat feature. If we go to a documentation for a specific function, there's an example here. And Cargo will actually compile examples against the current version of the code when you run cargo doc, and it will refuse to generate documentation if the example doesn't compile. So that's kind of a neat feature. If you see an example, you know that it may not be right, but it does at least compile as it's written. And that's the last bit of sort of the ecosystem and tooling that I wanted to go over. If you have any questions about that specific part, now is the time to ask them. I'll give you 10 seconds. I found this really cool cup, by the way. It's like a mason jar, and it has a handle on it, which I don't know, for some reason just makes me really happy.
Hey, Jayshua, I'm going to ask you a quick question. Are you recording the session on your end using OBS or something?
I am using OBS, but I'm not recording it.
I'm kind of finding that the screen share resolution is a little bit low.
Okay. I can try switching out.
If you try switching to screen sharing through Zoom directly, it might improve the video quality.
Let's give it a shot.
Much better.
Okay. Good.
Thank you.
All right. So second half. So Rust kind of started with an observation back when it was first invented, I think in 2008. And it started with an observation. And that observation was that the most common source of security vulnerabilities in modern applications is memory safety violations. And that's sort of an umbrella term which refers to things like using the same chunk of memory after it's been freed, or freeing the same chunk of memory twice, or if you have one chunk of memory, writing off of the end of it a buffer overflow error because it's not as big as you thought it was. These all sort of fall under the umbrella term of memory safety. Interestingly, that hasn't always been the case. If you go back far enough, memory safety violations weren't the most common source of bugs. Prior to memory safety, it was actually misuse of the goto statement. And if you read Goto Considered Harmful by Edgar Dijkstra, which you should, it's a very, very landmark paper in the history of programming. You'll find that in that paper, Dijkstra advocates for what ultimately replaced the goto statement, and that's structured programming. And we pretty much just view structured programming as programming today. Structured programming was replacing goto with things like if statements and for loops and while loops and do while loops and switch statements and so forth. Prior to the structured programming movement, we didn't really use those. And it's kind of interesting to look at what happened during that transition, because if you if you compare what we ended up with structured programming with what we had before Go2, you can see that we have new ideas which are simultaneously more complex and less powerful than what came before them. So they're more complex because there's just more concepts. Before all you had to know was Go2, but now you have to learn if statements, you have to learn for loops, you got to learn while loops, you got to learn do while loops. So they're more complex. They're also less powerful. There are certain programs that you can write using Go2 that you can't write using the new structured systems. But we sort of collectively decided as an industry that the trade-off was worth it because it eliminated a lot of the bugs that came up through misuse of the Go2 statement. So jumping back forward to today then, our new problem is memory safety violations. And Rust's question is it possible to solve those issues? Is it possible to solve those issues at compile time without any runtime overhead? We have solutions to most of them. These types of errors don't generally pop up in Java or C# or JavaScript because those languages are garbage collected. But garbage collection has overhead, and Rust wants to know if it's possible to solve the problems without that overhead. And it turns out that it is, and there's a lot of similarity to its solution as to Go2, the way Go2 was solved, because Rust introduces new concepts which are simultaneously more complex than what we had before and less powerful. Since they're new, you got to learn them, and this is probably the reason a lot of people get hung up on these points when learning Rust. So we're going to talk about those now. The two new features that Rust introduces are the concept of ownership and of lifetimes. So we'll start with ownership, and hopefully by the end of this, you'll be prepared to start learning Rust while getting over that initial difficulty that a lot of people have with these two concepts. So to start with ownership, we need a basic understanding of how memory is allocated in a modern program. So if I allocate a 32-bit integer right here, that allocation is going to be put on the stack, which is sort of working memory for a function. We'll get a 2 on the stack, and then when we allocate another variable, this will also go on the stack right here underneath it. And then the same thing happens as we call functions. If I call another function, that also gets put on the stack underneath. And then when the function goes out of scope, which happens right here, the stack entry for that variable will leave. And then when main goes out of scope here, these two stack entries will be automatically removed. And that's great. There's no memory vulnerabilities. If this was all we had, we wouldn't have any memory safety problems because we're not responsible for allocating and freeing memory. It's impossible to forget to free memory because it just happens automatically. Unfortunately, it's not quite powerful enough because you generally need memory to outlive the life of a function. So that's why we have the heap. And the heap is, my pen isn't working. The heap is where we allocate additional memory. So if we do that, I will create an array. So this X is now going to be a 32-bit array. Rust calls them vectors for reasons that probably make sense to somebody. So when this code executes, we will get an entry on the stack. It'll have a 3 in it, which is the length of our vector. And then it will also have a pointer into the heap, which is where the memory is actually stored. And the reason we do this is because we need data to outlive our function. And also, sometimes we need to allocate more than a couple of megabytes of memory. You can't allocate large chunks of memory on the stack because of the way it works. But now we have an issue. And the issue will show up if we take a look at what this code would look like if I were to write it in C. So this is an allocation on the heap of an array of integers, 4 of them. And at some point, we're going to have to call free. And that's where things start to go sideways. So what happens if you forget to call free? Then your memory is just sitting there, and you've never freed it, and you have a memory leak. If you call free twice, then you have the double free error, which we talked about. So you might give the pointer to somebody else and expect them to call free, but they don't. This is where the source of a lot of issues come in. And that's what Rust tries to solve. And it does that by introducing the concept of ownership. Rust says, because the problem is that we don't know who's responsible for deallocating this memory and people forget, instead, we will do it automatically, and the person responsible for freeing that is whoever owns the data. In this case, the owner is that pointer that's sitting on the stack. So when X goes out of scope at the end of main right here, the heap entry that's pointed to by the pointer will be automatically freed and will go away. So this is great. This solves the memory safety problem, but it kind of just makes the heap an extension of the stack, and we're right back where we started. So to see that, if we call our another function and pass in our vector, ownership has to move at this point because the party responsible for deallocating our memory from the heap is going to now be X. Ownership moves along with variables as you pass them around. So before, this variable owned the data on the heap and was responsible for freeing it. But after calling another, now this variable is responsible, and the memory will be deallocated at the end of this function. And we can see that in action if we try and use X afterward. So I will just try and print it out to the console, and then we will see the error. So our error is that we are trying to use a moved value. So you can think of borrow as just use. We'll talk about borrowing in a second. So the value is moved on line 6, which Rust helpfully points out, and then we try and use it after it's been moved here. And this is where the sort of additional complexity comes in. This isn't an error that you would see in most other programming languages because they don't care about ownership of memory, but Rust is very careful to track all of it. So it's a very limiting system. We need to pass data around to other functions and use them. So Rust introduces a new concept. You're getting additional complexity. It's the concept of borrowing. Rather than passing ownership into another function, instead we'll just temporarily borrow the memory. We do that by taking a reference. So what we're saying here is that the another function is going to temporarily borrow this data, but ownership will remain with this variable right here. And so the memory will still be deallocated when this X goes out of scope. So now if we try and print, can't type today. Now if we try and print it out, our code compiles and works fine because ownership has not moved. And Rust knows that at this point, that memory will still be allocated because there is no way for this function to deallocate it. Since we took a reference, we didn't transfer ownership of the data. So this is great, but now we have another issue. And that issue will come up if we take a look at what happens to the heap when we take a reference directly. So we're going to say xref is a variable which contains a reference to a vector of 32-bit integers. And then we'll just point it at the referenced X, like that. And then we'll try and print out xref here. So this would work fine unless we try to mutate X in between. So let's look at the stack. We have two entries on the stack. We have one that owns the data, that's this one. And then we have another entry, which is just an additional reference to it. That's xref right here. If we push data onto the vector and the vector isn't large enough to contain it, then memory on the heap will be reallocated down here. And then this pointer on the owning entry will be updated to point down here. And now we have a dangling pointer. xref is now pointing to memory, which is not allocated. It's the incorrect amount of piece of memory. So Rust solves that by, again, introducing a new concept. Again, we're adding complexity here. The new concept is there's a difference between a reference that can be used to read data and a reference that can be used to mutate data. In order to make this reference able to mutate data, you have to mark it as a mutable reference. And the rule is that you can only ever have one mutable reference, or you can have as many immutable references as you like. And it should be pretty clear how that solves the issue, because if you only ever have one mutable reference to this data, then you can just update it and point it wherever you want because there's only ever one reference. Or if you have multiple immutable references, again, it doesn't matter because you can't change this pointer to point anywhere else. You can't change it to point down here because it's an immutable reference, and Rust prevents that from happening at compile time, which we can see in action if we try and run this. Oops, I forgot to include a semicolon. So here we're saying that we cannot borrow X as immutable because it's also borrowed as mutable. And that's the rule we just mentioned. You can either have one mutable reference or as many immutable references as you like. And then Rust helpfully points out where all the issues are. We're mutably borrowing it right here. The immutable use is used here. And then we're trying to additionally borrow it right here while the mutable reference is in scope. So Rust prevents all of that at compile time. And it makes it kind of difficult to write certain types of programs. It's very difficult to write a linked list in Rust because of this ownership system, particularly a doubly linked list, because you'd have to have two references pointing at each other, which isn't something that Rust's type system can generally deal with very well. However, Rust's proposition is that that trade-off is worth it. So the ownership system, as we just described, works great. It prevents all these errors, but it's still not quite powerful enough to write programs that we'd like to write. And so Rust introduces one other concept, and that's the idea of lifetimes. And ownership kind of makes sense. It's basically formalizing how you would typically use memory in C. It's part of the programming language. Lifetimes, though, don't really exist anywhere else. So they're kind of difficult to get a handle on. And we'll work through it by writing an HTTP request parser, sort of. We won't write it, we'll just pretend to write it. So the basic idea is to take this HTTP request and parse it into a struct. We'll have a URL for the string, and then a set of headers, which will be a hash map, a dictionary, from header name to header value, like this. And then we have to import this as well. It's part of the standard library. Hash map is part of the standard library, and you would import it with a use statement like that. So in our main function then, we'll go ahead and pull some data from a socket. We'll just pretend we get it as a string, and then we'll parse it into a request. Like this. So if we think back to our ownership model that we talked about, you'll notice that I'm passing in the data by value. That means ownership of the string is going to move into our parse function. So that's great. The other thing that will happen is that since ownership has moved and the memory that's pointed to by the data string is heap allocated, so we'll have an entry for the length, maybe 40 characters, and then a pointer into the heap. Ownership has moved into this function, which means this heap data that contains our HTTP request is going to be deallocated at the end of the parse function, which isn't ideal because that means in order to put data into our HTTP request, we have to copy it. So we'll have an allocation for the URL right here. We'll have an allocation for each header name. So 1, 2, 3, 4. 4 allocations there. 4 allocations for the header values as well. And then all of those allocations are going to be owned by this HTTP request struct. So when this variable in main goes out of scope at the end of main, that memory will be automatically deallocated, which is great, but we'd rather do it without reallocating all of that memory. We already have this memory available. It's sitting in our data variable that's already owned by the data right here in main. And we'd rather just create pointers, references into that rather than copying data around because, you know, who knows how big the data could be. That could be quite an overhead if you're writing a web server that's handling thousands of requests, tens of thousands or hundreds of thousands of requests. So we're going to change this from a string to a string reference. So now instead of having a string, we're just pointing to a string reference. It's no longer owned. It's owned by somewhere else. And this is where lifetimes come in because Rust doesn't know whether the memory pointed to by this reference is the same as the memory that's pointed to by these two references. They could be different. All three of them could be different, or they could be the same. Rust doesn't know. So we have to specify how that memory relates to each other. And we do that by creating a lifetime, which looks like this. So it's included in brackets because you can have multiple of them. If you need multiple lifetimes, they look like this. And you can name them whatever you want. They act kind of like variable names. You can put whatever you want in there. That would be a standard variable name. So we'll just use prime A for now. And then we'll mark up these references. Now this might look kind of weird, but hopefully it'll be clear in a second. We're saying that the memory pointed to by the URL here is the same as the memory that's pointed to by these references and the same as the memory pointed to by these references. So now if we update our parse function to work with these lifetimes, we have to forward declare them. This is just a declaration. That's the same as this HTTP request right here. This is just a declaration saying we have a lifetime. It's like declaring your variable. And then we're taking a reference in by data, and we're saying that reference points to the prime A memory. It has a lifetime of prime A. And we're going to return an HTTP request which contains references to that same chunk of memory. So let's think about what we just said then. We're saying reference is the same as the memory pointed to here, which links back to this reference here and is saying this memory is the same as this memory, is the same as this memory, is the same as this memory. So now Rust knows that when the memory that you're referencing here is deallocated, then it can also deallocate the HTTP request. It basically guarantees that the HTTP request you're returning from the parse function will not outlive its source data. It's impossible for this HTTP request to live longer or live after the data is deallocated that it's pointing to. Which means that if Rust had a free function to free heap allocated data, you could not write this and then this, because that means that the data being pointed to by the HTTP request would be freed and you would still have those references around and you could attempt to use them. This code would not compile if Rust had a free function, which it does, but you don't normally use it. The other option that you could do that you could use lifetimes to represent is if you have multiple pieces of memory stored in the HTTP request. So if the URL points to a different chunk of memory than the headers do, then we can specify that by introducing another lifetime. We'll call this prime B. And then we'll specify that the strings in the hash map are now prime B related memory. And then we have to update our parse function. You can imagine that maybe the socket data coming in will allocate memory for the first line of the HTTP request and then separate memory for the rest of them. And this is how you would represent that. If you have the URL data come in as the first argument, it's a reference to some string that's sitting on the heap somewhere. And then header data comes in also as a string, but this has a different lifetime, prime B. We specify prime B lifetime here, and then we put both of them into the HTTP request. And think of this sort of angle bracket bit as filling in parameters like you would on a function. The first one links to the first one here. The second one links to the second one here. And then the actual struct definition indicates which references in the structure each of those tie to. URL is the first one, and then the headers is the second. So what we just told Rust then is that this reference is the same as this data on the heap, and these references is the same as this data on the heap. And that allows Rust to keep track of when you can and cannot use data and when it needs to be freed, and prevents us from writing code which would allow this data to be deallocated before the HTTP request does. So if we try and return the HTTP request from main like this, it won't allow this code to compile because the data is going to be deallocated at the end of main, which happens down here. And then we're returning references to memory on the heap that have been deallocated. And that's basically ownership and lifetimes. So hopefully that will help you get over the initial hump of learning these concepts that a lot of people have when they're learning Rust. And if you kind of think back to Go 2, we had the structured programming. We introduced new, more complex concepts that were simultaneously less powerful. And that's kind of what we just did here. We have new concepts, ownership and lifetimes, which are less powerful than just using allocation and freeing statements like we used to in C. And, you know, is it worth it? Is that trade-off worth it? And that's something that you kind of have to decide for yourself. Rust says it is, and a lot of people agree with Rust, but maybe it's not for you. And that's about it. So if you have any questions, now is the time to ask them. There is one. Says, what are the best use cases for Rust, and how does it compare with other languages like Go? I did intend to talk about this if I had time. Rust started as a systems programming language. It was adopted by Mozilla pretty early in its life to write the Firefox web browser, Servo. In fact, I believe it's the PNG parser of Firefox is currently implemented in Rust. So it started out as a systems level language for writing things like operating systems and so forth. But because of the way the ownership and lifetime model works, you don't really need to worry about allocating and freeing data like you would in most systems level programming languages. And it really has a feel more like you would feel writing in, say, C# or a scripting language, because you don't have to worry about any of that memory management type deal. So that makes Rust pretty applicable to lots of different use cases. There's an operating system program in Rust. People are using it to write web applications because you can compile it to WebAssembly. I'm not sure I would recommend doing that yet. The tech isn't quite there, but you can do that. People are using it to write web servers. I have a web server that I'm running that's written in Rust. It's a GraphQL server. People are using it to write native applications. There's some people that are using it to write games. As for how it compares with Go specifically, Go has a multi-threading system built into it through channels, and that makes multi-threaded applications written in Go very easy to use. It uses green threading. Rust doesn't have any of that built in. However, it does have lots of libraries that allow you to do those types of things. There's one library called Acetec, which sort of clones the actor model from Erlang that lets you write little pieces of your application that run independently and communicate with each other with messages over channels. And I believe last time I checked, the Acetec HTTP server implementation is the fastest in the world right now, because Rust is a very low-level language that compiles to native code. And you can do all of this multi-threaded and memory-related manipulation stuff very safely because of the ownership model and lifetimes. So best use case for Rust right now, just about anything you'd want to use it for except for web applications, probably. But it really depends on what libraries might be available, because the ecosystem isn't as well developed as, say, C's ecosystem is. Do I mark this as answered? Has it been marked as answered?
I think I already got it.
Okay. Okay.
We do still have, what, 5-6 minutes? If anybody else has questions, now would be the time.
If you don't ask any questions, then I'm going to assume that the presentation was absolutely perfect and explained everything you needed to know.
In the example that you were showing, where maybe you would try to like return that HTTP request, how would you actually return data like that?
So ownership has to move with the variables that are owning it. So right here, we're saying that the string, which is this text here, is owned by data. And so that's going to be deallocated at the end of main. So the only way to return a reference to that data is to make sure that that memory outlives main. And you can do that by taking it as a parameter. So we're pretending that we're not actually, this isn't actually a main function. This is another function. So you would take it in as a parameter. So now the ownership of of this data is whoever calls main. So whoever is calling main owns the data that we're passing in, which is what we did with the parse function, right? So basically you have to move the ownership of the data one level back up in the hierarchy by taking it in as a parameter. That's option 1. Option 2 is to make HTTP request own the data itself, which is what we did first when we did this, because now the struct owns those allocations. And when you return it, the ownership will move along with the struct. But that had a bunch of extra allocations. You could also do this, where you have the data being owned by the HTTP request, and it has references back into itself, like that. That would be another option. That would keep you from copying the data, which would be good. But you would still have the ownership lying with the HTTP request struct, which means you could return it. Does that make sense?
Yeah, I think sort of. Thanks.
Okay, cool. Any other questions? No? Okay.
Have you worked at all with doing any of the WebAssembly things with Rust? I hear that being one of the popular uses right now.
I have compiled a WebAssembly program in Rust that said hello world in the browser. It's pretty cool because WebAssembly doesn't have a garbage collector, and so you can really only write WebAssembly code in languages which either don't have a garbage collector or include one automatically as part of the compilation. And so Rust is kind of like the perfect use case for that. Actually getting it to work is quite a bit of ceremony though, because you can output the WebAssembly really easily, but there's still some a bunch of JavaScript that you got to use in order to interact with like the DOM, because WebAssembly doesn't have native DOM access. It can only communicate with JavaScript through like a sort of channel type deal. So you have to have a JavaScript program sitting outside the WebAssembly that communicates with it and puts things in the DOM when the WebAssembly program asks it to. But that's about all I can say about WebAssembly, because I've only compiled like one application for WebAssembly with Rust.
Okay, thanks.